Hi, unfortunately again I'm having some microphone issues, so I will have to do it with a bad microphone. Today I want to talk about measurements and a slightly more general setup than discussed before. What we said last time is we might have a state, psi, and we might ask, given psi, we ask a question, well, are you actually phi? Right? We're not allowed to directly ask, are you psi? We can only ask, are you a given state or not? Well, then there was Born's rule that would tell us the probability at which this would happen. Born's rule. And Born's rule is basically a description of what the probability is that we'll get a yes outcome to this above question. And this probability is given by this inner product. And here we use this funny notation, the inner product absolute value squared. And we use this funny notation here, this Cat-Bra notation, or this Dirac notation. And this inner product squared gives us the probability that we'll see yes. In a lot of cases, one can think of this guy just as a column vector, and this guy here on the left as a row vector. Okay, so that is nice, and this is still very much true, Born's rule, but I want to rewrite it slightly different, which will turn out to make it a bit more general. And especially for quantum info, this other formulation will turn out to be more useful than just Born's rule. That being said, Born's rule still valid and is still useful in a lot of cases, but I just want to make this setup a little bit more general, and it will be a lot easier to work with in practice, especially when you're working with quantum info. Okay, so let me maybe write down the motivations for doing this more general setup. Sort of Born's rule really only applies when we are given, for example, n qubits, and we ask, are you, so when both psi here and phi here, they are both n qubit states. But a very reasonable question to ask is, well, let's say I give you a 2 qubit system, and now I just measure the first one. I ask the first qubit, oh, are you this or that state? So we'll be able to deal with that. So let me just call that measurements on a subset or subsystem, which is, I guess, a bit more physics terminology. And not only will be useful for measuring subsets and subsystems, with this new general formulation, we will also be able to describe what our post-measurement state will be. And sort of in the above case that I described here, the post-measurement state was kind of obvious. If I start with psi, and I now ask, oh, are you phi? And I get yes, well, then the post-measurement state is, of course, phi. But it becomes a bit more tricky if I have a state like this. So I take now this maximally entangled state that we saw in the last video. And now I might ask the second qubit, this guy, oh, are you plus? And if I get the outcome yes, then, well, I might be interested in what happens to my second qubit. In fact, this is really a very important part of understanding entanglement. If we measure part of an entangled state, what happens with the remaining part? So using this more general technique that I will discuss, we can calculate questions like that. And one thing that we won't discuss for some time at least is that there's even a more general form of measurement called POVMs, which are really the most general measurements one can perform in quantum mechanics. And I won't discuss these now. That's a little bit too general. Instead, we will only discuss so-called PVMs. I actually forgot what they stood for. I think projection valued measures, or yeah. But the important part is that these POVMs, they're more general, and in fact, they're the most general measurements one could perform in quantum mechanics. Well, why would one be interested in this? Well, of course, it's good to know sort of what the best thing is, or the most general things that we can do, assuming quantum mechanics. This is in particular true if we're interested in cryptographic applications. If we want to protect against some eavesdropper, then we need to be able to sort of understand what the most general thing is that an eavesdropper could do. And so that's one potential motivation for understanding POVMs. But again, we won't discuss POVMs, but this generalization that I'll discuss now is at least is sort of the first step towards the more general case of POVMs. Okay, hopefully that was enough introduction. Let's now move on to this more general setup. So let me just give you the definition of how we will define a measurement, and then I will try to motivate this later on. Definition. A measurement, M, consists of a collection of outcomes. Right? When we perform a measurement, we can get a number of possible outcomes. So this will be some set, which will be ordered, and the measurement outcomes correspond to so-called, well, they will turn out to correspond to matrices. And these matrices we will just label by P1, P2, P3, etc. Let's assume it's just some finite number for now. Okay, as I said before, these matrices, these P sub I should be matrices. And they have two constraints on them, basically. We want that all PIs satisfy this property. Let me move this to the bottom. So this is our first condition. So for all PIs, if I square them, I get back the original PI. For all of the PIs in my set M. Now there's one further condition. I want that if I sum over all the i's that I have, I want them to sum up to the identity matrix. So these are really the only two conditions. Okay, well, let's look at some examples. I'll just write some examples first, and we will then get into sort of motivating this. Example 1, it's going to be a bit of a trivial one. It's always good to consider those. I'm going to consider the set M that only contains the identity matrix. Well, it's simple to check that we satisfy this condition and this condition. Those are easy to check. Second example. Let me make a bit more space. So we have here, we have this cat bra of 0, and here we have the cat bra of 1. So again, as a reminder, this just means, well, this cat was, we could think of as a row vector, looking like this, and the bra version was just the transpose of that, or the conjugate transpose, so that gives this. Well, if you remember your linear algebra correctly, you'll see that this is just equal to this. Similarly, you can check that 1, 1 is given by this matrix here. Well, let's check the two conditions. You can check that if you square this matrix here, you get back itself. And same thing for this matrix here. You should double check that. So that gives us this condition here. And you can see that, well, if I sum these two guys, I get back the identity matrix. Okay, so I just gave two examples of measurements. Now let's sort of try to think of them physically, because now I just showed you examples of these measurements, but just from a mathematical point of view. Let's sort of try to understand what is happening on a physical level. Let's first look at this case here, the second example. Well, this won't surprise you, but I'm really here only asking, this corresponds to measuring in a 0, 1 basis. So I'm asking, are you 0 or are you a 1? Right, this is an example we've seen before, but now we have sort of a really more mathematically precise definition. What could this be, this first example? Well, this is a measurement where there's only a single outcome corresponding to the identity matrix. Well, if we perform a measurement that only has a sort of single outcome, then we're not really performing a measurement, right? Because we're not distinguishing anything. And when we perform this measurement, we always get back this guy here. So this is sort of the trivial measurement, the one that will always return out yes. Before we continue, I would like to have a quick intermezzo, and this relates a little bit to why this Dirac notation is so useful. So I said that this guy, if you write it out, it becomes this guy here. And I told you that you could check that if you square this matrix, you get back itself. Well, if you do these calculations just using linear algebra, it gets annoying quite fast. But it turns out this Dirac notation gives us a way to calculate this, or to verify this fact a lot faster. How to do that? Well, let's take this guy, and we're going to square it. So we're going to multiply it like this. Now, what this Dirac notation allows us to do is to observe that if we look at this guy here, these middle two guys, well, this is just an inner product, right? I here have just 0 with a bra on the left side and a cat on the right side. But we know that this is equal to 1. So this is equal to this. And since we know that the term in between brackets is equal to 1, we get this. But this is, of course, just what we started off with. So you can see that, now I wrote out all the steps, but this Dirac notation would allow you to double check these calculations a lot simpler. And sort of the way to see this is that in a lot of cases we might be working with matrices that might have a lot of zero entries. And then this Dirac notation is just a lot more simple. In general, I would highly recommend getting comfortable with this Dirac notation and with its tricks. It simplifies life a lot. Okay, so that was my quick intermezzo. I want to quickly go back to the previous definition and look again sort of physically at this. So we had these two examples that we looked at just before, but now I want to look at, and we saw that these examples satisfied these definitions and they sort of corresponded to natural measurements, namely measuring 0 or 1, or sort of the trivial measurement. Now, let's look at these two conditions. Why will we have the top condition? Well, this will become a bit more clear when we've discussed post-measurement states, but the way to think of this is that when I perform a measurement asking, oh, are you in a given state phi, and I get outcome yes, if I then measure again, which you can think of sort of being represented by this square here, I should get back the same outcome, right? If I measured state psi, and I measured it to be phi, and I measure again whether it's phi, I should get the answer that yes, it's phi. And so that's encapsulated by the first condition. How about the second condition? Well, the second condition, as you can tell, looks very similar to the following condition, where these p sub i's are now really probabilities. And this is then just a sort of normalization property, right? If I have a probability distribution, I want their sums, the sum of the probabilities to equal 1. And so that's basically what we see in the second condition. Except now in the second condition, we have matrices instead of numbers. That is really sort of the quantum mechanical flavor. Okay. Let's move on to post-measurement states. So this is also by definition, or I guess more of a postulate of quantum mechanics. But given some measurement m, we measure and we're given a state psi. We measure an outcome corresponding p sub I with probability Let me write this a bit more clearly. Oops. So I take my pi and I sandwich it in between the bra of psi and the ket of psi. We'll get later back to this why this should be the case. then if we see this outcome, then the post measurement state is given by let me write it slightly differently. So at the top, at the top, we just apply the matrix or the projector. Maybe to emphasize this property here, this top property here is called. It means that pi is a projector. So we apply the projector to our state. Then we'll end up with a new vector. And this vector will not be a state in general because it's not normalized, in the sense that if we look at, if we calculate this guy, so note that, well, sorry, let's write it out. Let's call this guy psi hat. Just add a little hat to it. This is not normalized. What do I mean by that? Well, I mean that if I calculate this quantity, it will not be equal to 1. And this was a sort of a normalization condition that we required previously. And so it turns out that the way to fix that is by adding, or by, sorry, not by adding, but by dividing by this quantity here. So that's a sort of normalization constant. When you think back about classical probability, there's also something very similar happening there. Namely, when we have a probability distribution and we condition on seeing a certain outcome, we take part of our probability distribution, that is sort of this part here, but we need to be careful because what we'll have in general after that won't be normalized, and so we have to add this normalization factor here. And so this is very similar to the classical case. And we see that quantum mechanics is just really a generalization of classical probability theory. Okay, so this describes our post-measurement state here. Let's try to see if this makes sense. Let's go to a familiar example. Let's say we take pi equals this guy. And let's say that psi is the plus state. Well, we know already what's going to happen. We know that if we're going to measure and we see this outcome here, we know that the post-measurement state should be the 0 state. And we know that the, well, okay, let's have a look at it first. Let's double check. So we apply this now to psi. Well, when we write this out, remember the plus state was 0 plus 1. Now you can also see the power of the Dirac notation. I don't have to write out the vector. I can just use the tricks that we know from the Dirac notation. So we apply 0 to here. Well, then we have bra 0, cat 0, right? So we just have this. But we know this is equal to 1. Okay, so the first part will just give us 0. And then we apply the cat or the bra 0 to this guy here, but that will be 0, right? Because we have that 0, 1 is 0. So we end up with this. oops, we end up with this, and we still need to have this factor here. And remember, this was just pi applied to psi. And as you can see, this guy is not normalized. So let's see if that gets fixed. So we now need to calculate this quantity here. Well, instead of calculating this, let me sort of prove to you what it should be. Well, we know that if we want this to be normalized, this factor here, we know that we should divide by 1 over square root 2. Or in fact, the same thing as multiplying by square root 2. So let's see what happens. Well, note that I can now make use of this projector property. So I can just add for free a pi here. Right, because you had that this was really the same thing as applying it once. Okay. But here and here I have this guy. Aha, but this is easy because this is just given by this quantity here. And I realized I made a mistake because this should be actually a square root. Let me actually double check that in my notes. Seems like I made a mistake. In the meantime, as I check this, let me try to multitask. So, of course, now what we discussed was the case just on a single qubit, but the main application of these more general measurements was that we could also describe the post-measurement state when we just measure a single qubit. So let's look at a specific example. And we're going to take our usual friend, 0, 0, plus 1, 1, our maximum entangled state. And we're going to measure, apply the following operator on it, or following measurement. Identity. Zero. And identity tensor 1. So just to emphasize, this tensor product here and this tensor product here is just the same tensor product we've seen before. However, previously we used it in the following context. We may have some state that is the tensor product of two individual qubits. That's really what this tensor product indicated here. It basically said, okay, we have a qubit on one side, which is in a 0 state, and another qubit which is in a plus state. Similarly, what this means here is that we perform some matrix operation, or really just some matrix where this guy here, the identity in this case, gets applied to the first qubit, and this guy gets applied to the second qubit. So this notation, or this notion of tensor products, allows us to not only describe individual systems, individual qubits, but it also allows us to describe operations on those individual qubits. Okay. Now let's see. Don't worry, I will get back to this square root thing, hopefully in a bit. But let's first look at some examples. So you should double check, by the way, that this measurement here satisfies the two requirements that we had above. It shouldn't be too hard to see. Okay, so let's apply this. Let's apply the first one, and I'll let you can see that the second one is calculated in a very similar manner. So in quantum info, what happens quite often is that we will be a little bit unclear with, or it will be implicit what we mean when we apply certain operators to certain qubits. So what we mean here is that this identity here will act on this qubit here, which is the same as this qubit here. Okay, so that's a little bit boring. But we know from what we saw previously that this guy will act on the second qubit here and the second qubit here. Well, we saw before that applying that to this guy here will sort of kill that part, because we had that 0, 1 was equal to 0. And it won't be too hard to see that this is just given by, we end up with 0, 0, up to some normalization, which I forgot here. In general, I should say, of course, this normalization constant is usually not the most important part, that one you can sort of just brute force, or just calculate by hand. So with normalization, we get out this. And then if we had to normalize that, this factor here would get killed, of course. So now we see that, okay, we end up with a really tensor product. Sorry, this is proportional to 0, tensor 0. So it seems that if we measure the second qubit, we see to be 0, we'll see that the first qubit will be 0. Now, you should check what happens when I measure these. So I now measure the second qubit, whether it's plus or minus. And then finally, you should check the following. What happens if we measure the second qubit to be this state, which I'll define in a bit. So I measure it whether it's I or minus I, where plus minus I is defined as very similar to the plus and minus state, but instead of there just being a plus or minus, I have an I here additionally, so an additional phase factor. So you should check what happens for these. And the answer might be a little bit surprising, actually. Okay, let's see if we can solve the solution, this normalization constant. Let's have a quick look. Let's try to see if we can do it on the spot. So if our post-measurement state is pi, applied to psi, up to normalization, then we want this to be normalized. In other words, if I now take the inner product of this guy with itself, then we want here some additional, let me make more space. So we're going to multiply here with some constant. Let's call it lambda. So we'll have this. If I were to be precise, I would also have to add a complex conjugate here. But if you think carefully about this, this won't be necessary. This has to do with the fact that, well, I guess we didn't talk about this, but if I have a state psi in quantum mechanics, then this is completely indistinguishable from a state that's the same up to some phase vector. So I now added some phase vector here in front of the state psi, and physically this is completely the same thing as having this guy here. Why is that? Well, that's for the very simple reason that if I have a state psi and I want to calculate the probability, I'm now going back again to the Born rule, it's a little bit easier to see there. If you want to calculate the probability that I'll see a state phi, then this is completely the same whether I multiply with this phase factor. Why is that? Well, because you can see that this phase factor cancels out. Or I can write it as follows. But a phase factor, when I take the absolute value squared, I get back 1. You should double check to see for yourself why that is. There's a nice geometric interpretation of this. And so these phase factors don't matter. This turns out to have a lot of very interesting consequences in quantum mechanics, and this really sort of leads to some very deep and fundamental properties of particles, which obviously I do not have the time to talk about now. But yeah, there's some interesting physics and mathematics that relates to this property. Anyway, that being said, I can remove this complex conjugate. In effect, I can rewrite this to be lambda value squared, and well, since it's real, it's just lambda squared equals to bra psi pi pisa pi psi. Let's see. And we should take the absolute value squared, I guess. Well, this is just equal. We can kill these two pi's, so we just get lambda squared and so we see that this leads to lambda being equal to let's see, it turns out this will always be a real number, I believe. Yes, this should always be a real number. And so we see that lambda is equal to, indeed, this guy. So let's double check where I made a mistake here then. Because here I thought there should be a square root, or at least I did that to sort of compensate for my mistake. Oh yes, of course. Yes, silly. Well, let's just use this calculation here to see it a bit more clear. Here, this part in green gives us this part. But now here we just have psi. So that is just this part. And in particular, we don't have this part here now in purple. So we see that this is incorrect, and this should be just 1 over square root 2. And that is exactly what we saw that we needed. Okay, well, it's good that I had my notes correct, but I just made a silly mistake. Either way, I hope that was a little bit helpful. This was just very much an introduction to measurements and how they lead to post-measurement states. I would really suggest that you go through these examples here. And also these ones here. And in particular, try to use this Dirac notation as much as possible. The fact that we write things as matrices is very nice, but in a lot of cases, especially when we do calculations by hand, this Dirac notation is really invaluable. And it just simplifies life a lot and allows you to communicate a lot faster also with other people in the field. When you go on to writing code that does simulations, then you might write out whole matrices. But when you do calculations by hand, the Dirac notation is very useful, so it's good to get some practice with that.